Hi everyone, welcome back to PW English Medium channel. Friends, my name is Subrat and I welcome you all to UMEED NEET English Crash Course series. In this series, we are completing each chapter for NEET 2025. In this chapter, we are going to talk about all the important concepts, some numericals and some PYQs, right? So today's class is going to be about magnetism and matter. Friends, if you haven't watched moving charges and magnetism yet, please watch it before starting this chapter, right? It has already been uploaded. You can find that chapter in the playlist. So let's quickly start this chapter. See, today we are going to talk about, we will start with bar magnet. We'll talk about the magnetic field produced by a bar magnet, and we are going to talk about, in the later part of the chapter, we are going to talk about magnetic materials, their properties, their classification, and last topic is going to be magnetic hysteresis. Please note, I don't write all of the topics in the first slide. So we are going to cover almost everything. So don't worry, we are going to, when I'm talking about magnetic materials, we'll discuss about paramagnetic, diamagnetic, ferromagnetic, their differences, each and everything. Curie's law, everything will be completed, right? Nothing will be left. Now to start with, in this chapter, first let's talk about magnet, right? We all know what magnets are. Magnets, when we are talking about the magnets over here, we are discussing the bar magnet, right? Now what do we mean by bar magnet? What do different things we know about bar magnet? We know that bar magnet has got two poles, and if we place two unlike poles in front of each other, they attract, and if we place two like poles, they repel. So there's a force of repulsion and attraction similar to what we have seen in charges also, right? Is acting in over here also. Now what we are going to actually say is, we are going to define some things. First, we are going to define strength for these poles, for north pole and for south pole. We are going to define those as by pole strength. So basically, let's say that north pole has got pole strength of plus m and south pole has got pole strength of minus m. So this pole strength is doing nothing but it is telling you the strength of the magnet, the strength of the pole, right? So we have got two equal magnitudes of pole strength and of opposite polarity, and let's suppose the separation between these two poles is, let's say it is L. Let's say it is L. Right. So now after defining pole strength was just, it can be plus m or minus m. Now we are going to define something which is called as magnetic dipole moment. Magnetic dipole moment. Acha, while explaining magnetic dipole moment, let me also tell you that half of this chapter, when we are going to talk about magnets, its magnetic field at different points, all of those things are very similar to what you have learned in electrostatics, right? So whatever you have learned in electrostatics about electric dipole moment in an uniform external electric field, work done on an electric dipole moment, torque acting on it, everything is going to be similar over here. We are going to just say it is analogous to whatever you have learned in electric dipole moment. So it will be a good revision for all of you, right? So when we say magnetic dipole moment, we have already defined one definition of it. In the previous chapter, we said that magnetic dipole moment was nothing but m equals to I cross A, and direction was found using right hand rule, right? Over here we are going to say now magnetic moment is, because we are talking about that it is analogous to what you have learned in electrostatics. Magnetic moment is going to be the product of magnitude of pole strength of any one of the pole times the distance between them, and because it's a vector quantity, we'll also write an L cap over here. So this L cap is actually a unit vector along south to north, right? So that means the direction of dipole moment is something like this, south to north. For any sort of magnet that you are going to talk about, from south to north, it would basically means something like this. This is the direction of magnetic dipole moment. And we have already talked about the magnitude. So direction is going to be something like this, right? So this is going to be magnetic moment m into L dot I cap. In electrostatics, we used to write it as Q times D. Q was magnitude of charge, D was separation between them, right? Now after this, if you have got this particular part, let's also define what do we mean by magnetic field. How you are going to define magnetic field? There was one definition that we learnt we discussed about magnetic field in the previous chapter. We said that if you have got a moving charge particle in a region and the path of the charge particle changes, or a force acts on it, or a moving charge particle experiences a force, that region is said to be having magnetic field, or magnetic field is said to be that region, right? Over here we can define it like the magnetic force experienced by a north pole of a unit pole strength. Now please see, this is also completely analogous to what you have read in electric field. If you remember, in electric field, the thing which is analogous, I'll write it over here for you. Electric field intensity was defined as force experienced per unit charge. Force experienced per unit charge. So here as well we are saying that magnetic field will be defined as magnetic field intensity, magnetic field, or magnetic field induction, right? So it has got three names. So it is defined as the force experienced by a unit north pole. That means a north pole which has got a pole strength of unit, 1 magnitude. And by the way, what's going to be the unit for this thing? You can find out the unit by using simple thing, that unit for magnetic moment is using that formula. We can write it as ampere per ampere meter square. So for this one, the unit is going to be ampere meter. All right. So over here we have got magnetic force divided by m naught. So this is a very important formula. We are going to use it quite often. Now at anywhere, if you want to find out the magnetic field, you can, so see what we are talking about. Let's suppose we have got a source over here. We have got a source. That means we want to find out the intensity of magnetic field of this source at any point, at any point P. Let's say at distance r. So that's what we are trying to do right now, right? And that's why we are going to talk about a point source also. So this this will be in Tesla or Weber per meter square. You know all of these things, right? Force is in Newton. I've already explained what is going to be the unit of m naught. Now before moving on, let's also talk about some of the properties of magnetic field lines. That will be really important. And why we are doing it? We are doing it because first let me also draw a bar magnet for you. So let's suppose I've got a bar magnet, something like this. And let's say we have got plus m over here. That means this is north pole. I've got minus m over here. That means this is south pole. So magnetic field in between of these two is going to be from north to south. From south to north, and outside the magnet it will be from north to south, right? And never two magnetic field lines are going to intersect each other. So now this becomes, okay, just a second. Yeah, something like this, right? Although you can draw this diagram, you can draw many more magnetic field lines, but it's, you know what we are talking about. So I leave after this, something like this. So outside the magnet field is from north to south. Everyone knows this. So this is just a formality, right? Outside the magnet fields are from north to south pole, while inside the magnet it is from south to north, right? Magnetic field lines are closed curves. So this is a difference, as when we are going to compare it with electric field lines. Electric field lines were in open loops, right? They appear to converge or diverge at poles. The number of magnetic field lines originating or terminating on a pole is proportional to its strength. So this is very important. More number of magnetic field lines means there is more magnetic field intensity at that particular point, right? So if you have got north pole and south pole of two different magnets which are placed near together, magnetic field lines are going to be something like this. And if you have got same poles, magnetic field lines are going to repel each other. Magnetic lines of field can never intersect each other, because if they intersect at a point, intensity at that point will have two directions, right? Similar to what you have learnt in electric field also. So at any point, if you want to find out the direction, you just make a tangent like this. So at this point, the magnetic field will be in this direction, right? So no two magnetic field lines can intersect, because then it will have two directions, which is not possible. Magnetic lines of field tend to contract longitudinally. So this is something that is called as contracting longitudinally, like a stretched elastic string when opposite poles are here. So something like this. It is contracting. That means it is coming together, something like this, and over here it is repelling each other laterally. That means when you are going to have similar poles or like poles, it's going to actually repel. So please remember these diagrams also. Some more few properties, and then we'll quickly move to some numericals. In a region of space when there is no magnetic field, there will be no lines of field. This is why at a neutral point, so at neutral points, magnetic field intensity is 0, right? There can't be any line of field. Magnetic lines of field originate from or enter the surface of magnetic material at any angle. So this is also a difference as compared to what we have learned in electric field. Magnetic lines of field exist everywhere, inside everywhere a magnetized material. As monopole do not exist, the total magnetic flux linked with the closed surface is always 0. So this is nothing but this is Gauss law for magnetism. So B dot ds for a Gauss law for a closed surface will be 0. All right. So after this, now let's come back to some other points. Let's suppose we want to find out the magnetic field due to a point source. So we have got a point source over here. This is a point source, and we want to know the strength of the magnetic field at a certain point from here. Let's say at this point, point P, right? So, and it is at distance r. So this magnetic field is actually written as mu naught upon 4 pi, and let's suppose it has got pole strength of plus m, mu naught upon 4 pi m upon r square. This is going to be the magnitude of magnetic field, right? And direction you can find it out. If it is plus m, the direction of magnetic field at this point is going to be something like this. All right, so this is very, very important, and again analogous to what you have seen for electric field. Electric field was k q by r square. So every time when you are going to talk about magnetic field, now k, that was 1 upon 4 pi epsilon naught, will in this case will become as mu upon 4 pi, mu naught upon 4 pi, where mu naught is the permeability of free space, right? So hopefully everything is clear till this point. Now see, when we are going to talk about a bar magnet, let's suppose we want to discuss bar magnet, and we have got north pole over here, so plus m. We have got south pole over here, minus m, and we want to know magnetic field at two different points. One is, let's say, at this point, and one is at an equatorial point, let's say at this point, right? And one we can also write it for a general point. Again, we are going to derive it similarly to what we have derived it in electric dipole moment. Now please, if you want me to actually again, if you want the derivation again, I would suggest you to watch the electric field chapter all over again. I have actually derived each and every derivations. Okay. So over here we'll just write it as in the form of 2a, right? And at this particular point B net will be actually in the direction of something like this. So this will be axial magnetic field. This is going to be axial magnetic field. So do you remember how we wrote axial magnetic field in the case for electric field? Electric field axial point was written as 2K P upon R cube, isn't it? Let's say this is also from midpoint, this is also R. This is going to be A. So this is R. So this is going to be R minus A. So in this case, B axial will be written as, just by using the analogy, just by comparing it with electric field, it will be, see, instead of K, we'll write mu naught upon 2 pi, mu naught upon 4 pi. By the way, that was 4 pi everywhere. If have I written 2 pi anywhere? Yes, everywhere it's 4 pi. Okay? Mu naught upon 4 pi times 2 times of, instead of electric dipole moment, it will be magnetic dipole moment upon R cube times m cap. So m cap is actually the direction from, n cap is actually the direction from minus m to plus m. So this is the direction of magnetic moment, right? So that's what we are seeing over here. Hopefully everything is clear. We don't need to derive this thing because derivation is very, very easy. Now if you want to know at the equatorial point, we can, at least we can draw the vectors over here. If you will talk about it, we'll say, okay, we know what this distance is, we know what this distance is, right? So magnetic field due to this one is going to be in this direction, magnetic field due to this one is going to be in this direction. Let's say angles are theta, so net magnetic field is going to be in this direction. So at this point, net magnetic field will be something like this. That is equatorial point, right? So, and if you all also remember, for equatorial point, magnetic field was minus Kp upon R cube. So this will become, over here also, if you closely see, magnetic field at an equatorial point will actually become minus mu naught upon 4 pi m upon R cube and m cap, and that is what we are trying to say, that direction of magnetic moment is in this one, but the net magnetic field will be in this direction, for a simple reason that they will these vertical components are going to cancel out each other and horizontal components will add up, something like that. Hopefully everything is clear with this concept. These are the two formulas that you will often use, and if at all, if they talk about at any general point, we'll simply say B net is actually equals to mu naught upon 4 pi R cube m 1 plus 3 cos square theta. Please have a look and compare this thing also with what you have learned in electric charges and fields. Moving forward, now if this dipole is kept in a uniform magnetic field, right, in an external magnetic field, and by the way, this external magnetic field right now is uniform, that means magnitude. Acha, let's also talk about what do we mean by uniform magnetic field. So this type of magnetic fields are uniform magnetic fields, which are equidistant from each other, right? I'm trying my best to make them equidistant. So these are known as uniform magnetic field lines, where direction as well as magnitude are all same. Other than this, if let's suppose you have got magnetic field lines like this, so these may be, I mean, I tried to make them as equidistant, but still direction is not same everywhere, right? Direction is not same everywhere. Or something like this. Here direction is same everywhere, but they are not equidistant. So at this point they were equidistant, at least I mean you must agree with me that I tried that it is equidistant. Here they are not equidistant but direction is same. And another case you can have both the things, like for example as direction is also not same and they are also not equidistant. So all of these cases are for non-uniform magnetic field. All right. So now with this, let's move back to our topic, magnet in external magnetic field, and right now I am considering this to be a uniform magnetic field. So if we are talking about uniform magnetic field, and let's say we have got a bar magnet, something like this, and you have got north pole over here, you have got south pole over here. Now see, everything is similar to what you have seen in this one, but still I'll explain it. Just tell me, if we are talking about a uniform magnetic field, this is external uniform magnetic field, can we assume that we have got north pole over here? We are just assuming that magnetic fields must be producing from a north pole and they must be moving towards some south pole, right? So that means this particular pole will experience a force something like this, which is going to be, force is going to be dosto m times magnetic field B, and this one will experience a force towards north pole and this one will be m times B as well, right? So if you will ask me what torque, see net force on this dipole is going to be 0, so there will be no change in the translatory motion. So if net force is 0, net acceleration will be 0. Everything is similar to what you have learned in electrostatics. So that's why I'm not really explaining each and everything. In short, if you are going to ask me how you are going to write net torque over here, so net torque will be written as F times R perpendicular. Let's suppose that this vector, which vector I am talking about, this vector is making an angle, theta with the magnetic field, right? Which vector? Dipole moment. Magnetic dipole moment is making an angle theta. So we are going to say MB, because these two forces are making a couple, MB times let's say the distance between them is D, so it will be D sine theta, right? Now M times D is your magnetic moment B sine theta, or what you can actually write it in vector form is torque equals to M cross B. Everything is similar, I have already told you, so not to worry about anything. Right? Now if someone says that what is going to be the work done in rotating this dipole, right? Work done. Acha, by the way, what that magnetic field is trying to do, that magnetic field is trying to align the magnetic dipole along its length, along its direction. So work done in rotating bar magnet. If you know all of these things, switch to 1.5x, quickly skim through over all of these topics. We'll then quickly come back to some questions also. Now work done, first of all we'll say that there is a small work done in rotating the bar magnet by small angle d theta. And if you want to find out the net work done between two angles, all you need to do is you need to integrate this thing. Let's say you want to rotate it from theta 1 to theta 2. Now again same thing will happen if you integrate mb sine theta with respect to theta. Integration of sine theta will be minus cos theta. So the work done, the net work done is going to be mb cos theta 1, because you have got a minus sine minus cos theta 2. So this work done will be stored in the form of potential energy of the dipole, right? So this is going to be the formula for potential energy as well. So potential energy can be written as minus mb, or not yet. Let's suppose we are talking about at different angles. Let's say at let's say that theta 1 was 0 degree, right? And we have rotated it by theta 2 is actually theta. So what is the work done? So that whatever the work done is, it will get stored in the form of potential energy. So that potential energy will be written as minus mb cos theta, or for this specific case we can write it as minus m dot b. So now again we'll talk about the same things we have discussed in electrostatics. That is, there are going to be two cases. One is going to be stable equilibrium, right? One is going to be stable equilibrium. For stable equilibrium, we are going to simply say that potential energy is going to be minimum, and minimum potential energy is actually minus mb at theta equals to 0 degree. And then we have got unstable equilibrium, and unstable equilibrium is actually when potential energy is maximum, and maximum would mean plus mb, and this will happen at theta equals to 180 degree. Hopefully everything is clear till this point. All right. Also, we are moving it very slowly, right? We are moving it very slowly. That's why we are not talking about kinetic energy. So this is a very important point, that work done in rotating a bar magnet very slowly. So now let's come back to some of the questions over here, and I would highly suggest you to pause the video, do it by yourself, and then check it. Okay? Because else there is no use of these classes. If you know something and still you want to watch it at 1.5x, quickly move to questions, quickly pause it, try to solve it in max 1 minute, under 1 minute, try to solve it, then unpause the video. A bar magnet having a magnetic moment of, we have got a bar magnet whose magnetic moment is given as, so whenever they say magnetic moment, it means capital M, 1 into 10 to the power minus 4 joule per Tesla. What type of unit are they talking about? So they have used, and just digressing from the topic, they have used that torque can be written as mb sine theta. So m can be written as torque upon b sine theta. So torque is actually nothing but Newton meter, that is, you can also write it as joule, and this is Tesla, so joule per Tesla, right? So not to worry about, you can also use this as unit. Is free to rotate in a horizontal plane. So if it is free to rotate in a horizontal plane, what do we mean by this? Let's suppose this is a horizontal plane and this is a bar magnet, and it is hinged by an vertical axis, and it is free to rotate about this, something like this, let's just say, right? A horizontal magnetic field exists, that is B is actually equals to 4 into 10 to the power minus 5 Tesla. Find the work done in rotating magnet slowly. See, so whenever they talk about slowly, we don't have to worry about kinetic energy. In slowly, from a direction parallel to the magnetic field, that means if they are saying parallel to the magnetic field, this means that they are saying that theta 1 was 0 degree and then theta 2 is 60 degree. So theta 2 is going to be 60 degree. So very easy. They have talked, we have already discussed what work done is going to be. Work done is going to be minus mb cos theta 1 minus cos theta 2. And by the way, if we have written cos theta 1 over here, it will become plus. So m was 10 to the power minus 4 into 10 to the power minus 5. Cos 0 will be 1 minus cos theta 2 is going to be 1 by 2. So this will become 0.5, right? This will become 1 by 2. So this will be something like 8 into 10 to the power minus 9 joule of work done is needed. Please have a look, check. Acha, one mistake, sorry. This is actually 1 by 2, so this will become actually, this will become 2. So 2 into 10 to the power minus 9. That's going to be your answer. Now let's move to the next question. Hopefully everything is clear with this one. Next question says a magnet of magnetic dipole moment capital M is released in uniform magnetic field of induction B. So see, this is all magnetic field of induction is just magnetic field intensity B from the position as shown in the figure. Find its, okay, so from this figure we have to find out the kinetic energy at 90 degree, right? So it has been released from this position, and when it will make an angle of 90 degree, because magnetic moment will try to rotate the bar magnet, we have to find out the kinetic energy at 90 degree. So see how to do problems like this. First, if you want to find out the kinetic energy at 90 degree, apply the conservation of energy. Conservation of energy for two angles, that is from 120 degree to 90 degree, right? So at 120 degree, we know that there is no kinetic energy. All what you can also say is, it's very easy, that change in kinetic energy will be actually equals to negative times of change in potential energy, because there are no other forces. So finally the final kinetic energy minus 0, that is initial kinetic energy, is equals to initial potential energy minus final potential energy, because you have got a minus sign over there, right? So initially kinetic energy was at 120 degree, potential energy will be written as minus, by the way, that's written as m, so it would be minus m b cos 120 plus m b minus m b cos 90. So this will be 0, right? Cos 120 is nothing but minus 1 by 2. So this will be plus mb by 2. So that is going to be your final kinetic energy at 90 degree. Hopefully everything is clear. Now second, what is going to be the maximum kinetic energy? When you are going to talk about the maximum kinetic energy will be maximum. Kinetic energy will be maximum where potential energy is minimum, isn't it? Now at which point potential energy is minimum? So potential energy is minimum at theta equals to 0 degree. So now again let's apply the conservation from 120 degree to 0 degree, right? So at 120 degree, again we are going to write, finally the kinetic energy will be minus mb cos 120 plus mb cos 0. So this will be minus mb by 2 plus mb. Please see once again. If you have any doubt, let me know in the comment section. Acha, this will be also plus, because cos 120 is minus 1 by 2. So this will be plus 3 by 2 mb, and of course kinetic energy will always come as positive. Now you tell me if you have any doubt in the comment section. Okay, everything's clear. Conservation of energy funda is all good, concept is all good. All we are doing is change in kinetic energy is equals to negative time. So that means loss in kinetic energy is gain in loss in potential energy is gain in kinetic energy. So after this, let's move to some new questions. They can also ask you question like this, that find the net magnetic moment. Now over here what they are trying to do is, you have got two magnets of similar pole strength. We need to assume similar because nothing has been said, है ना? So let's say for this bar magnet, dipole moment will be in this direction from south to north. In this will be from south to north, and if they are of similar magnitude, net magnetic moment will be 0 because they will cancel out each other. And we are just assuming that these are nothing but these are M, and they have actually said that it is M. Oh, they have said, they have drawn it as M. For here it will be, the net magnetic moment will be from south to north, so they will add up. These are vector quantities. These are vector quantities, so they will add up, and the net magnetic moment in this case will become 2m. Very easy, normal vector addition, and direction is going to be from south to north. Over here, see, these are also quite simple. This is M, this is M. So the net magnetic moment will be in this direction, which will be at 45 degree, which will be M root 2. So M root 2 is going to be your answer. For this one, dosto, it will be M net will be, I am explaining using the formula, or you must be knowing this, how to write it directly. It will be M square plus M square plus 2 M square cos 60. Hopefully everything's clear. M square plus 2ab cos theta. So this is going to be M root 3. Let me know if you have any doubt in the comment section. Now, after this, we are going to actually talk about a certain point which we have also again discussed in electric charges and fields. That was neutral point for electric field. Here the neutral point would mean that a point where net magnetic field will be 0. Where net magnetic field will be 0. That is what is called as a neutral point, right? So for example, if you have got a bar magnet, right? At a bar magnet, let's say this is plus M, this is minus M, and they are at a separation of D. So at their midpoint, you have got a neutral point, because if at this point we'll be having a neutral point over here. Think about it. Think about it. Are we going to have a neutral point over here? See, instead of taking this as an example, if you remember, I have drawn one more diagram over here like this. So this thing can be considered as a point where net magnetic field will be 0, right? Or what you can also do is, sometimes they also use the Earth's magnetic field. So that's not a problem. Wherever they will ask you to find out the net, to find out the neutral point, this must be the condition. That means the net magnetic field at that point must be 0. All right. So after this, now let's talk about our next topic, which is actually about magnetic materials and their properties. And the first property that we have got over here is magnetization. Now, before moving to magnetization, just now we discussed in detail, we discussed about magnetic dipole moment. So magnetization can be defined as of a sample is equal to the net magnetic moment per unit volume. Now, what do we mean by this? So by saying a sample, let's suppose we have got a material, and this material has got dipoles, first of all, they have got atoms, and those atoms has, let's suppose, dipoles in this random direction. So when we are talking about the magnetization sample is equals to the net magnetic moment, this net magnetic moment, this definition is more accurate. It could be permanent or it could be induced magnetic moment per unit volume. All right. So if you are going to take a unit volume and you will find out what magnetic moment is, so that means M will be written as magnetic moment. Right now I am writing it as M divided by volume. So this will be called as magnetization. Now before starting the class, before starting this topic, let me tell you that there are two types of material in general. I'm not talking about ferromagnetic or paramagnetic. I'm talking about a classification that we are going to learn before that. There are two types of material. One is in which the individual atoms do not have magnetic moment. So the individual atom itself do not have the magnetic moment. And another type of materials are in which the individual atoms have magnetic moment, but they are randomly oriented. Acha, what will happen if they are oriented in one direction? If they are oriented in one direction, they will start behaving like a magnet. That's what makes a magnet a special material, right? So the individual atoms have magnetic moment. Now after this, we are going to categorize all of those three materials that you have been reading about, dimagnetics, paramagnetic, but we'll come to it, right? So first of all, what do you mean by magnetization? If someone is saying that this material has lots of magnetization, it means that per unit volume there are more atoms which have got dipole moment in one direction, right? So if let's suppose I have got two in a place, let's suppose I am talking about this as a unit volume, and I have got here two atoms whose dipole moments are like this. So they will cancel out each other. Net magnetic moment of this sample will become 0. So net magnetization will become 0. So we will say it is not a magnetic material. It is a it has no magnetization, we will say. Okay? Now first thing is should be absolutely clear, that is capital M. It is called as magnetization. It tells you the density of, or it tells you the intensity. I mean, don't get confused with the word intensity. It tells you how many magnetic moments are there in per unit volume, and those magnetic moments can be permanent or they can be induced because of some another field. We'll talk about that as well. Now before starting this chapter, again I'm saying starting this particular part, let me say that we have got a solenoid over here. We have got a solenoid and this solenoid is, let's suppose that this solenoid is kept in some external magnetic field. This is some external magnetic field, and this external magnetic field is, let's suppose this is B. Alright, this is an external magnetic field. And let's say right now, assume one case in which there is no material inside. Alright, there is no material inside. Also you can assume that, okay sir, let's suppose that it has also got some wires and current is flowing in it. So it will have its own magnetic field, and that magnetic field can be considered as mu naught Ni that you might be knowing about, right? Now what I am saying is, if you want to find out the net magnetic field of any material, of let's suppose of this material, net magnetic field. Now we are saying that also assume that we have got some another material which is inside of this material. It's not air or vacuum, we have got some another material inside of this, inside of this core, which is kept in an external magnetic field. So the net magnetic field will be equals to two things. One is because of the exterior part, that is the applied magnetic field, which in this case was B external, and one is going to be due to the induced magnetic field. One is going to be due to the induced magnetic field, right? Now we can actually say that, sir, if let's suppose we have got an external magnetic field. that external magnetic field B naught can be actually written as in the form of mu naught Ni, can be actually written as mu naught Ni, or even if you are not understanding this thing, let me explain one thing. Let me explain once again this particular topic. See, we are not right now saying that B net will be greater than B naught. B net will be greater than B naught or less than B naught, because this will actually define the types of materials we are going to talk about. So if B net is greater than B naught, we are going to say we are talking about a particular type of material, let's say paramagnetic or ferromagnetic. If B net is less than B naught, we are going to say we are talking about another type of material, let's say diamagnetic material. So let's start from here. So we have got a magnetizing field, so this will be also called as an external magnetizing field, because of which we are now hoping something will happen to these to the magnetic moment of these individual atoms, right? Now they might get aligned towards the external magnetic field. So let's suppose you have applied an external magnetic field something like this. This is external magnetic field. Now your dipole might align something like this, or your dipole might align something like this. There can be two things. Your means I'm talking about the atom over here. Alright. So now let's again come back to our diagram. Now please see here. Acha, one more thing. This intensity of magnetization that we have written, this is actually, let's write it as I. Usually it is being written as I. So I'll write I over here, and this will be magnetic moment divided by volume. That will work, right? Acha, you must not have any problem in unit. Magnetic moment has got unit of ampere meter square. So this will have a unit of ampere. This one has ampere meter square. Magnetic moment is right, ampere meter square. This one is meter cube. So intensity of magnetization has got unit of ampere per meter, right? Now let's again come back to our diagram. So we said that let's suppose we have got a solenoid which is having a current I, something like this, right? So it will have a magnetic field mu naught Ni, that is because of external reasons. So mu naught Ni. So now what I'm going to say is this B naught can be actually written as mu naught times Ni, because this is all because of internal factors. Sorry, this is all because of external factors. That is because of current. Right? Now think about it. We can also define a term which will be actually written as B naught upon mu naught, which will be called as H. And further this thing can be written as this H is actually nothing but it is magnetizing field. It is actually magnetizing field. What do we mean by that? Let's understand. I'm giving you another example. Let's suppose you have got an external magnetic field over here, which is actually B naught, right? You have an external magnetic field over here. This is B naught. Now this B naught is also containing an information which is the medium. So if someone tells you that sir B naught is actually equals to mu naught times Ni, it also holds the information of a medium. I don't want that. What I want is, if I place two materials over here, if I place two different materials over here, I should actually get to know what is the difference between what is going to be the difference in magnetization because of a certain physical quantity which is independent of material. So that's why we have defined a term which is H, which is actually magnetizing material. So this is the importance of this, that this H is actually independent of medium. Independent of medium. Right? So if you are going to talk about any other medium, so H can be written as magnetic field at that point divided by permeability, absolute permeability of that medium. This can be written as something like that also. right? So this was the internal factor, this was the external factor that we are talking about. It can be considered as a magnetizing field. H is considered as a magnetizing field. By the way, what's going to be the unit for H? It is going to be just H can be also written as N into I. That means unit of H will be ampere meter, because ampere per meter, because this is total number of turns per unit length. So again, this is going to be same unit as intensity of magnetization, right? So hopefully everything is clear till this point. Done. Now next thing is induced magnetic field. Acha, induced magnetic field will be directly proportional to intensity of magnetization. Why are we talking about this? Intensity of magnetization. I'll explain. See, right now I don't know when I'm going to apply the magnetic field. I don't know whether the magnetic moment of individual atoms will align themselves along the direction of magnetic field, but in the opposite. I don't know that. But I can surely say that this factor, which is the internal factor, will be more if there are more number of if there are more magnetic dipole moments they are getting aligned. In whichever direction they aligned, I don't have a problem with that. But if they will be more, this factor will be more, right? So I can say that induced magnetic field will be directly proportional to intensity of magnetization. That means Bi will be can be written as equals to mu naught times I. So while simply write the magnitude, I have now two things. Initially, I have written that the net magnetic field will be the vector sum of external magnetic field and induced magnetic field. Now B naught can be actually written as mu naught Ni, and Ni can be written as H. So this thing can be written as mu naught times H. So this is one of the thing. Another thing is Bi can be written as mu naught times I, where I is the intensity of magnetization. So if I'll plug both of these things over here, net magnetic field will be equals to mu naught common, that will be H plus I. Have a look. Most of the students have a problem in this. If you are still having a problem, please rewind, play again and think about it. Now I'll do one thing. I'll take H common. So I'll be having B equals to mu naught H times 1 plus I by H. Now again one more thing. This I by H also we are going to call a particular name for it. Think about it. What is I by H? What is I by H? So now when we were discussing about this magnetic field, and we said, yeah, let's have a term which is independent of material medium. So we said that instead of this B naught, let's just call it as H, that is magnetizing field. That is magnetizing field, right? Now let's suppose that there is one magnetizing field and I've got two materials. Over here in same magnetizing field, and I'm seeing that in one of the material there is more intensity of magnetization. What does it mean? That there are more dipole moments getting aligned, or dipole moments per unit volume is more than the other, right? So that means if I'll say that in A it is more, so I'll say that intensity of magnetization per unit magnetizing field in A is greater than that of intensity of magnetization per unit magnetizing field in B. We'll call this as magnetic susceptibility. It will be easier for us to communicate. Now again, short thing. If I'm keeping these two materials in a same magnetic field, in a same magnetizing field, and this one is getting more magnetized than this, so I'll say that this is more magnetic susceptible, right? So this symbol that is known as Xi is known as magnetic susceptibility. So magnetic susceptibility is nothing but this thing is called as magnetic susceptibility, and formula for this one is going to be I by H, and because I and H have same unit, this is a dimensionless quantity. It just tells you a number. So if this has got magnetic susceptibility of 10, another material has got magnetic susceptibility of 50, you know what it means, right? Now coming back to our topic, if this is the case, I can rewrite this thing as B by H equals to mu naught 1 plus magnetic susceptibility psi, and B by H again can be written as absolute permeability equals to mu naught times 1 plus psi. So these are, see, all of these formulas are important. Right from these things, all of these formula holds great importance. And now you can find out the relation between absolute permeability of any medium equals to mu naught equals to mu r. So this mu r is actually nothing but mu divided by mu naught, also can be written as 1 plus psi. All of these formulas are very important. Hopefully everything is clear now, right? Now we are going to discuss the three types of materials. What are the three different types of materials that we have got over here, right? So hopefully everything is clear till this point. Now when we were talking about this classification, now let's again come back to it. So individual atoms do not have any magnetic moment. These types of materials are known as diamagnetic material. And these types of materials have another classification in which we have got two another types of classifications, which is paramagnetic and ferromagnetic. Now let's start one by one. First, let's start with diamagnetic. What is the definition of diamagnetic material, or the main property of diamagnetic material? They have a tendency to move from stronger to weaker part of the external magnetic field. This basically means that diamagnetic material repels magnetic field. So instead of getting magnetized, instead of getting attracted to a magnetic field, it is getting repelled by it, right? So a diamagnetic material, a magnet repels diamagnet. The resultant magnetic moment in an atom of a diamagnetic material is zero. That's what we have started our class with, right? Sorry, this topic with. Acha, examples are very, very important. Bismuth, copper, lead, silicon, nitrogen and STP, water and sodium chloride. Extremely important. In NEET, NTA can ask the examples, right? Acha, before moving on to all of those things, if we are talking about a diamagnetic material, what we are trying to say is that this B net will be actually less than the applied magnetic field, isn't it? Because it is getting demagnetized, not demagnetized, but it is getting magnetized in the opposite direction. That's how it is going to repelling the external magnetic field, isn't it? So if this is the case, we are going to say, if this is the case, we have just written something like this, that B upon H was equals to mu naught times 1 plus magnetic susceptibility. Now think about it. If this value is less than 1, this value should also be less than 1. Or think it in different terms. This is absolute permeability of that medium. This is absolute permeability of a particular free space times this is actually written as mu r. Now we know that if diamagnetic material is getting actually magnetized in opposite direction, we can say one thing, that mu will be actually less than mu naught. And if that is the case, we can say that mu r will be less than 1. Also, magnetic susceptibility will be negative because it is only possible in this case. So negative, and it will have a small value. Now we can talk about every other part over here. in diamagnetic materials also, superconductors are some metals which are cooled to very low temperature, which exhibit both perfect conductivity and perfect diamagnetism, in which magnetic susceptibility is -1 and relative permeability. This thing is actually known as relative permeability. This is known as relative permeability. Relative permeability will be 0. That means mu will be 0, right? A superconductor repels a magnet, and by Newton's third law it is repelled by the magnet also. The phenomena of perfect diamagnetism in superconductor is called as Meissner effect, and it is also used in those levitating trains, right, that you might have seen in on Nat Geo or Discovery or somewhere, right? So coming back to, so that was the diamagnetic material. We have not completed diamagnetic material. We'll again come back to it when we'll be comparing all of the three materials. But coming back to paramagnetic, now you know that paramagnetic are going to be attracting it, but the thing is, they attract the magnetic field, but they weakly attract it, right? They weakly attract it. They have a tendency to move from weak magnetic field to strong magnetic field. They get weakly attracted. The individual atoms possesses a permanent magnetic moment. And again, examples are very important: aluminium, sodium, calcium, oxygen, and copper chloride, right? So please remember the examples over here as well. Another thing is, see, now what we are going to see is an important law, which is Curie's law. Curie laws basically says that magnetization of a paramagnetic material is inversely proportional to the temperature and directly proportional to the applied magnetic field. So C is going to be a constant. So M will be equals to C B naught by T, where C is a Curie's constant. This is Curie's law. Curie's law hold good for temperature and not for strong magnetic fields, right? So you can also rewrite this thing as, you can rewrite B naught as, by B naught, if you remember, B naught was nothing but mu naught times H, right? So if you will write over here mu naught times H, you can actually get to magnetic susceptibilities formula as well, right? So hopefully everything is clear till this point. Now moving on to ferromagnetic materials. Ferromagnetic materials, what is the difference between ferromagnetic materials and paramagnetic? This is very important. Before starting this particular topic, we have got two types of materials. One is paramagnetic and the another one is ferromagnetic. So let's suppose this is a ferromagnetic material. And this one is a paramagnetic. So we know that individual atoms have got permanent dipole moment, something like this. But when there is no external magnetic field, the net magnetic moment of the entire sample is going to be 0. Obviously, same thing is going to be true over here as well. The only difference is that over here we have got some things that are called as domains. What are these things? These are basically some regions where magnetic moments are in one direction. Still the net magnetic moment is going to be 0, but if you will something like this, hopefully you have understood it. Still they are going to cancel out each other and it will become 0, but the thing is, when you are going to apply an external magnetizing field, it will be a lot easier for an external magnetic field to align these dipoles in one direction. So the extent of magnetization in ferromagnetic material is far greater than a paramagnetic material. So it got weakly magnetized, this gets strongly magnetized. So this is the difference. So Ferromagnetic substance, those which get strongly magnetized when placed in external magnetic field, they have strong tendency to move from weak to strong region. Individual atoms possesses a dipole moment. In non-uniform magnetic field, the sample tends to move in strong region of magnetic field. Everything similar. See, now in ferromagnetic materials also we have got two types of different materials. We have got hard ferromagnets, which are also known as permanent electromagnets, or from hard ferromagnets we can make permanent electromagnets, and another ones are called as soft ferromagnets. Now, hard ferromagnets are referred as permanent magnets, in which magnetic materials that retain the magnetization even after magnetizing field is removed. We are going to talk about it in hysteresis, but the examples of these are going to be are 𝐿𝐂𝐃, alloy of iron, aluminium, nickel, cobalt. So this basically means that even if you have actually removed the external magnetic field, the retention of magnetic character is going to be quite large, quite big. Whereas in soft iron, we are not saying that it will completely become demagnetized when we'll remove it, but the retention is going to be really small, right? So soft iron or magnetization disappears on removal of external magnetic field. Examples are iron, cobalt, nickel, gadolinium, etc. The relative permeability is greater than 1000. Now let's talk about some of the other important points. You will see this diagram quite often, right? And I think in NEET also they have asked diagrams like this. Think about it. This is the external magnetic field. So this is the magnetizing field H. And what are we seeing? That this magnetizing field is getting slightly repelled by the media, by this block. So this block has to be a diamagnetic material. So for a diamagnetic material, magnetic susceptibility was negative and small. Relative permeability was less than 1. Absolute permeability was less than mu naught. It is getting attracted, magnetizing field is getting attracted, but feebly getting attracted. So this one is going to be paramagnetic. So for paramagnetic, magnetic susceptibility is positive but small. Mu r is slightly greater than mu naught. Okay, over here also mu r is, mu r is slightly greater than 1, or mu is slightly greater than mu naught. When magnetizing field is strongly getting attracted towards the material, this is going to be called as a ferromagnetic material. Alright, so in ferromagnetic materials, we know that magnetic susceptibility value is positive and large. So you will have big values of psi, and then you have got relative permeability will be far more greater than 1, and absolute permeability will be also far more greater than mu naught. Alright, then some of the graphs as well, dosto. Let's also see the graph. Now you tell me, what is this? This is intensity of magnetization. That means this is magnetic moment per unit volume. And we are seeing that on increasing H, we are having a negative I. That means M must be negative, right? For in this case, M is coming out to be negative, which basically means that if you are applying magnetizing field in this direction, then magnetic moment are getting aligned in opposite direction, isn't it? So this is the case for a diamagnetic material. For a diamagnetic material. Acha, by the way, this is nothing but this I upon H, the slope is going to be psi I by H, and that's what we said, that it's going to be small and negative. So graph is going to be like this. That means as you increase H, magnetization will increase but in opposite direction, right? This is going to be paramagnetic. And this is going to be ferromagnetic, in which this relation is non-linear. And why we are seeing something like this? Because at this point we are saying that saturation has been achieved. At this particular point saturation has been achieved. That means at this particular point almost all atoms magnetic moment is aligned. Right? Acha, now we have got something like, we have got graph of magnetic susceptibility and temperature. We are seeing that this is constant and negative. That means again this is going to be a diamagnetic material. Small and constant. You can see that the slope was constant, right? So this thing is going to be a constant. Got it? So the relation between magnetic susceptibility and temperature for a diamagnetic material is that this remains constant with respect to temperature. Very important. And in Curie's law we saw that for paramagnetic materials magnetic susceptibility was inversely dependent on temperature and directly dependent on magnetizing field, right? Whereas in ferromagnet also same thing will happen, but the only thing is that this will have large values. See, so these 6 graphs were very important, and we have done nothing. We have just revised whatever we have studied till now. Hopefully everything is clear till this point, right? Now let's look at some one or two questions also. By the way, this is from PYQ. Paramagnetic substance align themselves along the direction of external magnetic field. That's correct. Attract strongly towards the external magnetic field. So this statement is wrong. It attracts weakly. Has susceptibility little more than 0. This statement is also correct. Move from a region of strong magnetic field. This is also wrong. So the correct answer should be option with statement A and C. So A and C, that means option D. So see, my motive of today's class was as quick as possible. Let's quickly revise all of this at this entire chapter. Right. So we again every time I say that we are going to talk about just numericals in another series also. Right. So this is for a quick revision. These one shots are for quick revision. Moving on to another question. Match the column. This says paramagnetic susceptibility. Paramagnetic susceptibility will have it can't have one is for superconductors. So one is for superconductors, right? Diamagnetic substance has magnetic susceptibility less than 1. Ferromagnetic substance has magnetic susceptibility far greater than 1, and this one is when relative permeability will be greater than 1. Hopefully everything is clear, right? So with match the column we have revised many things. Acha, hard ferromagnetic materials are characterized by, we are talking about hysteresis loop. So first let's cover hysteresis loop, then we are going to talk about it. See, acha, one more thing, the ferromagnetic property depends on temperature. At high enough temperature, a ferromagnetic becomes a paramagnetic temperature, and this temperature is known as Curie's temperature. This temperature is known as Curie's temperature, right? And also remember it for iron, it is around 700 degrees Celsius, right? The temperature of the transition from paramagnetic to from ferromagnetic to paramagnetic is called as Curie's temperature. So you can also write this law that magnetic susceptibility is inversely proportional to 1 upon T minus Tc. Here Tc is the Curie's temperature. For iron, I told you it is around 770. For iron, right? For iron, Tc is 770 degrees Celsius. Hopefully everything is clear with this point also, right? This is known as Curie-Weiss law. So now moving to hysteresis loop. Hysteresis, so first of all, let's talk about what does this term hysteresis means. because it's not like we are going to only talk about hysteresis in this chapter. Hysteresis is a common term which basically means to lag behind, which means to lag. Now, why we are using it over here? We are using it over here because let's suppose you have got a magnet and you have kept this magnet into an external magnetic field, or we should say we often say it into an magnetizing field H, right? And let's suppose its dipoles started to getting aligned, something like this. So after a certain period of time, and of course with increasing H, so if you are going to increase H, what will happen? If you are going to keep on increasing H, M will increase. Is that clear? We have seen this, that I is actually directly proportional to H, and I by H is actually a constant, which is actually magnetic susceptibility. So as you are going to increase H, magnetization will increase. At a certain point, all of these magnetic moment will get aligned in a particular direction, right? Now let's suppose we want that again, we want to demagnetize it. So what we need to do? What we'll do is we'll actually start to remove all of these fields. We'll start to actually remove this, and we'll see that after removing this, we were only able to remove some of the magnetization. Still, some of the magnetization is in the material, and that is why hysteresis is only talked about only for ferromagnetic materials. It is only for ferromagnetic materials. All right. So these are the some of the magnetic moment which are still intact by removing the magnetization also, magnetizing field also. So this is known as retentivity. So if you are going to draw a graph on this, a graph will look something like this, and I'll explain it. So the graph was started from this point, and we have seen that, see, initially, if you will again go back to our graph, do you remember that initially this graph was something like this, that I with respect to H is going to be something like this. By the way, this graph is between I and H. So here the saturation has come. So again, coming back to the hysteresis loop, so we are increasing the intensity of magnetization. So at the very start, we are just drawing this graph. Okay? So it is increasing something like this, and at this point saturation achieved. That means at point A, all of the magnetic dipole moments were aligned in one direction. Now we are actually decreasing the magnetizing field, and we saw that it did not actually retraced its original path. It took a new path. That means when we started to decrease H, I was not following the same values. And when H was again 0, at this point when H was again 0, there was still some magnetization left. This property is known as retentivity. Now things like hard ferromagnets like for example as steel has more retentivity than soft iron, which is a soft ferromagnet, right? But now you will say, but still sir, I want to actually demagnetize it. So I'll suggest that, okay, now apply magnetizing field in opposite direction. So it will again, now it will actually destroy these magnetization also. So that's why we have got graph in the negative direction now. So this property is known as coercivity. So coercivity basically tells you the strength of magnetizing field in the opposite direction to demagnetize the material completely. Now let's suppose, why do we use in some cases, most commonly in cores, we use, wherever we are going to talk about cores, we use soft iron. Why? Because soft iron has got low retentivity. That means if we want it to behave If we want it to behave like a magnet, we can make it behave, and when we don't want its magnetic field, we can actually quickly demagnetize it, and we can also, the retentivity will be small also. So low retentivity and low coercivity. So if let's suppose this is the graph of steel, soft iron will have low retentivity, so it will be a shrinkier graph. That means for steel it is a broader graph, and the height will also be a little less, right? Hopefully everything is clear till this point. So again, if you will again if you will again keep on applying the magnetic field, it will every dipole will get magnetized in the opposite direction. By the way, this is only for ferromagnet. Then again, if you will do the same thing, this is going to be the graph of hysteresis, right? And the area under this graph, area under hysteresis loop gives you the loss of energy per unit volume. Acha, why there will be loss of energy over here? Bhai, you are applying magnetizing field, and when you are removing it, it is not coming back to zero. You need to actually give more magnetizing field in opposite direction to demagnetize it. That means there will be a loss, right? And if you want to completely demagnetize it, what you will do, again you will place it like this. So there will be more loops, something like this, till it becomes completely demagnetized, right? We can draw that graph also, but it's fine. I mean, if you want me to draw, it will look something like this. That again at this point, it will be something like this. So it will keep on shrinking, something like this. All right. And then it will finally become demagnetized. So this is known as demagnetization. Then again and again you are repeating the cycles to completely demagnetize it. Hopefully dosto, everything is clear and you are enjoying it. So the hard ferromagnetic material is categorized by a broad hysteresis loop because it has got more retentivity. Then next, the magnetic moment of paramagnetic. See, these are the some of the types of question that you are going to see. You are not going to see a very complex problem. The only difficult thing about this chapter is that you must memorize, you must remember all of these things till your NEET final exam. That is the most important thing, right? Because you have got many things. When you will talk about all of these things in between of your preparation, you will think, sir, very easy, I'll do it some afterwards. But they'll ask you a question like amongst bismuth, copper, aluminium and oxygen, which one are of this type of material, which one of different. So you will miss it at that point if you haven't revised it, right? So I'll suggest you to go through the theory of this again and again. The magnetic moment of paramagnetic materials is what? It is actually, if you are going to talk about the entire a particular atom, it is going to be constant but low of an atom, right? So please note this thing. And if you are going to talk about the entire material, because I mean they might say about, like for example, as they'll say this is a ferromagnetic, this is a paramagnetic material, what about this? So it would be 0. So noting this thing, that material is something which I am saying that this is the material, that means the whole of sample. So we should actually take the answer as 0, not constant, right? Moving on, if the relative permeability of a material is this, that means relative permeability is less than 1. That means relative permeability, which is actually nothing but mu upon mu naught, it is less than 1, which means mu is less than mu naught. This means that we are talking about a material which is which is actually getting magnetized in the opposite direction, which is nothing but a diamagnetic material. When a magnetic substance is heated, then it loses its magnetization, right? It loses its magnetization. So dosto, hopefully everything is clear till this point. Hopefully you enjoyed this lesson. I wanted it to keep it short and crisp so that you can quickly revise it, right? Again, I'm again and again saying in these one-shot videos, we are not specifically talking about just numericals. There will be more series in which we'll just talk about numericals, right? Those will start by March. But that will be all for today. Thank you so much. Have a great day and keep preparing for your NEET 2025 exam. All the best. Thank you so much.